Hi there. In this lesson, we're looking at optimization problems, something that you have tackled in previous years. We're going to have a look at it again, perhaps with some more technical problems. As usual, optimization problems are all about finding a maximum or minimum value given a particular scenario. And of course, in the calculus unit, we're using calculus techniques in order to find that maximum or minimum. In terms of the steps, just to remind you from previous years, the first step is a literacy step. That's what I call it anyway. And what I mean by that is you're reading through the problem for understanding, that you understand each of the words, what it's looking for. You understand what the constraints are. An optimization problem will always contain a constraint, a limitation that you need to factor into your problem solving. And also you need to work out what is it that you're trying to maximize. Is it a volume? Is it an area? Or minimize? So just be mindful of that. If you can, and if it's relevant, draw a diagram is your second step. The third thing is use your constraints and what you are looking for to model the problems. Almost always there's two variables in the model, and you have to reduce it down to one variable by considering the constraint. And we'll go through a problem in a second so you can see that. And then finally, I'll just zoom out so you can see it here. Use the model to answer the questions in the problem. Now, the question could be as simple as find the maximum or find the minimum, or it could be find the value of the function at this point and draw a graph here and whatever else. But ultimately, once you've got the model, you should be able to work things out pretty straightforwardly from there. You can see I've got some dot points there on slide 2 there. Use calculus to work out that maximum or minimum. I suggest where possible use the second derivative test to confirm that it is a minimum or a maximum. It's really important that you do confirm that it is, unless in an exam situation it says you don't need to, then you should do it. Also keep track of how many marks the question is worth. If it's worth 2 marks, maybe you can get away with not confirming it. But if it's worth more, you should definitely confirm it. And again, you're allowed to use the first or second derivative test, but I suggest the second derivative test by default. And lastly, please don't forget that there is a potential that if you're finding a maximum or a minimum over a restricted domain, the maximum may be at an endpoint, not at a stationary point. And I've got an example of one here. I don't know what the function is, it doesn't matter. Maybe it's a roller coaster ride. And you're asked to find the maximum height of the ride above the ground. And if you use calculus, you would come up with that as a maximum. But remember what I said a few lessons ago, that's actually a local maximum. Across from 0 to 100, although that is a local maximum, we can see just visually that at 100 meters, the roller coaster ride is above that of the local maximum here. So calculus wouldn't necessarily uncover that. So you basically have to ensure that you test for endpoints if it is not obvious that the local maximum is also what we call the global maximum as well. Let's get stuck into a question. And look, there are so many different optimization problems with so many different angles. It would be impossible for me to cover every single possible way. The best thing you can do really is look at past exams, past test papers, get a feel for the kind of optimization problem that is being asked. And then, I know I say it over and over again, but it's important for me to say it once more. Practice, 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 dot, 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 practice, 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 practice to the nth power. Okay, that's really, the more you do, the more quickly you can scan through a problem looking for the information that you need. The more likely you're going to come across a problem that you're going to be able to say, oh, I've done one like this in the past, etc. Just comes down to that ultimately in the end. But for this video, the example I'm going to go through is from the textbook, and I'll just show you which one it is. It is example 23 from this section. I think it's 10F. Yep, 10F. And let's have a quick look at it. I'm not going to rewrite it, so if you need to pause this video and write it into your summary book, please feel free to do so, or at least put a reference to example 23 in section 10F. So we've got a cylindrical tin canister closed at both ends, has a surface area of 100 square centimeters. Find, correct to 2 decimal places, the greatest volume it can have. And then you've got an additional, if the radius of the canister can be at most 2 centimeters. Find the greatest volume it can have. Okay, so there's two things we need to find: the greatest volume, and we've got the greatest volume possible, and then with an extra constraint of 2 centimeters for the radius, what the greatest volume would be under those circumstances. Okay, so let's go about sketching this. Sorry, I didn't mean to sketch it, I meant to solve it. So I've just started the problem up on the next slide. I'll just zoom up for a bit. So you can see here, you don't necessarily have to write this down, but you need to be able to at least mentally identify some of the things from the paper. So there was a constraint that the surface area has to be 100 square centimeters. We were asked to optimize the volume. So they're the two things we're looking for. And there was a second constraint, wasn't there? The radius had to be 2 centimeters, but that was an additional section to the question. It said first find the maximum volume given a surface area of 100 square centimeters, and then secondly find the maximum volume given a radius maximum of 2 centimeters. So just be mindful of that we need to, we've actually got a two-parter there, even though it didn't say A and B. You can see then I've gone to draw a diagram. Again, do you have to do a diagram? No. But why do I suggest you do it? And why do all math teachers suggest you do it? It's because what we are trying to do is chunk down your thinking into small bits. So thought number one, do I understand the question? Thought number two, can I identify the bits? Oh yeah, surface area, 100. Okay, cool. Thought number three, what does this look like visually? And you can see here I've got my diagram of a cylinder, which I have then blown out to a flattened net of the cylinder so that I can start readily identifying the surface area from this diagram. Why? Because I know my constraint was 100 square centimeters. Now, looking at this in a bit more detail, you might just see that the tops here are the circles here, really rough. That's all you need. And I've identified there's a radius measurement there. The height here is the height here, so that's where that came from. And 2 pi r, you could sort of imagine that if I wrapped this rectangle around the circle here and the circle here, the circumference of this circle would in fact be the length of that rectangle. So we've got 2 pi r. Okay, with all of that in mind, let's have a look at solving this problem. So we start off with it doesn't kind of matter where you start off with, but looking ahead, the constraint almost always allows you to take the two variables that you might have in the equation and eliminate one of them. So in this case, we've got height and radius, and we are going to make radius the independent variable. So we're going to try and effectively eradicate height from our volume equation, which we haven't set up yet. But let's start with the surface area then. So I'll just leave this all zoomed out so you can see it as I go. So the surface area is going to be those two circles. So we've got 2 lots of pi r squared. That's the two areas of the circles. Plus, we've got the area of the rectangle in the middle. And one of the lengths was 2 pi r, and the second length was h. And so the area of the rectangle in the middle is 2 pi r h. And our constraint says this whole thing needs to be equal to 100. Okay, now what I'm going to do is I'm going to express h as the subject of the equation. So we're going to have h equals something at the end of it. So I'm just doing my best to isolate the h. So I can see a common factor of 2 pi r there. So that'll leave me with r in the first term and h in the second term. And that's equal to 100. Divide by 2 pi r to get 100 over 2 pi r on the right, and then h is equal to 100 over 2 pi r minus r. And that would be okay, although just thinking ahead, I reckon it's going to be easier if I have a common denominator. So it's going to be 100 minus 2 pi, oops, I've missed a step, haven't I? We can divide top and bottom by 2, and that will give us 50 over pi r minus r. And now I'll find a common denominator of 50 minus pi r squared all over pi r. So I've just multiplied that second term by pi r, top and bottom, to make a common denominator. Okay, so there is our work there. And we are now going to work out the volume, and we know the volume is pi r squared h. And we are now going to eliminate the h out of the volume formula by replacing with that big old formula that we had, or expression for h, we just worked out. So we've got 50 minus pi r squared over pi r, like so. Now we can see the r will cancel out one of the r's here, and the pi's will cancel out. And so we end up with r outside of 50 minus pi r squared. And then if I expand that, I'm going to get 50r minus pi r cubed. So there we go. We now have an expression for volume which is entirely in terms of r. No h's to be seen. So now we can maximize the volume, or consider the maximum of the volume, by finding the derivative. So dv, the rate of change of volume with respect to dr, the change in r, is equal to, and I'm just going to find the derivative of that volume, which is really straightforward. It's going to be 50 minus 3 pi r squared. And because we're looking for a stationary point, we're going to set it equal to 0, and we're going to solve there. So we're going to have 3 pi r squared is equal to 50. I'm going to have r squared is equal to 50 over 3 pi. And so we've got r is equal to plus or minus 50 over 3 pi. Like so. So that's it. They're our stationary points, but of course only one of them is valid in the context. So that means that r, which is approximately equal to plus or minus 2.3, I can now say that r is approximately equal to positive 2.3, as r has to be greater than 0. So there you go. We've got our r coordinate, if you like. Now we're going to do our confirmation. This proves that it's a maximum. So we look at the second derivative. So I'm going to use d to v dr squared notation there, our second derivative. And if I have a look back, I can see that my derivative is 50 minus 3 pi r squared. So I just need to find the derivative of that for the second derivative. And I get, well, the 50 will disappear. So I'm going to get minus 6 pi r. And that at r equals 2.3, we can see that dv by dr squared is going to be less than 0, isn't it? Because 2.3 is positive, so it's got a minus times this, which is positive, is going to give us a negative number. Don't care what the actual value is. It is clear by inspection, if you like, that d to v dr squared is less than 0 at, I put it next to, didn't I? At r equals 2.3. So I can say, therefore, there's a maximum at r equals 2.3. Okay, great. So we've used the calculus to work out where the stationary points are, and we've confirmed that for r equals 2.3, it's a maximum. Now we are going to go back to our volume equation and work out exactly what that volume would be then. So therefore, max volume at v equals, and I'm just doing a substitution, 50 times 2.3 minus pi times 2.3 squared, and that is equal to 76.78 cubic centimeters. That is our maximum volume. Okay, quick graph. If we graph this, and we could use our GDC to graph this if we wanted to, but we can also use our understanding of how graphs work, we are going to get a function which looks a bit like that, probably a bit too steep the way I've drawn it. Here is going to be 2.3, 76.78, like so. Here is going to be the square root of 50 on 3 pi. Not that that's particularly essential to know, but nevertheless, there you go. So there's our domain. The domain here is the radius has to be between 0. I'd actually use round brackets because we can't really create a cylinder if the radius was actually 0. So the radius has to be between 0 and root 50 on 3 pi. So that's what the domain is. How did I get root 50 on 3 pi? Go back and have a look and see if you can figure it out for yourself. It's pretty easy to work out the r-intercepts on this graph. So this is v versus r. So it's a really quick graph. And then we can sort of see that 2 is going to be basically here somewhere. So if 2 was our actual maximum in the domain, then we can see that at 2 it would be a maximum volume as well. So I can then say if maximum radius is at r equals 2, so it's a restricted domain now, or even more restricted, I suppose, then we have v equals 50 times 2 minus pi times 2 cubed, and that is equal to 74.87, I think, cubic centimeters. And when I went what I'm trying to say is that I didn't actually, I prepared this beforehand. So what I would have done at that point, of course, is got out my calculator and put the values in order to solve that fairly quickly. So that's it. So we've answered all parts of the question. We've got the values that we need, and we're good to go. Your turn now. Do as many as you can. Practice, 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 practice.